the general principle of relativity in its philosophical and historical aspect by Herbert, Wildon, Carr. Chapter 8. The Modern Scientific Revolution and its Leaders. It is curious that we should associate the maxim hypothesis non fingo with the scientific method of experiment, and suppose that the making of hypotheses is a particular vice of speculative metaphysics. The exact contrary is true. It is the scientific experimenter who makes hypotheses, and it is no reproach to his method that he does so. It is its essential feature, and by no other means can he advance. On the other hand, it is the philosopher who vitiates his method the moment he proceeds to make hypotheses, for the assumptions he introduces into his premises will assuredly reappear in his conclusions. It is the philosophers, of whom we may take Descartes and Hume as types, who are entitled to inscribe on their banners Newton's often quoted motto. This does not mean that Newton was vainly boasting. He was indeed a true philosopher in his simple and direct acceptance of fact, his disregard of its conflict with accepted theory, and his attempt to interpret it without any respect for preconceived opinion. I shall endeavor to show that Einstein, in his formulation of a new theory of gravitation, in this respect follows his great predecessor, for the new theory is not a hypothesis, it is the acceptance of paradoxical facts in spite of the paradox, because they are based on experience and confirmed by experiment, and the formation of a principle in conformity with them. It will be well to begin by stating in definite and positive terms what the new principle is, without reference to the experiments which have called for it. The relativity principle of the classical mechanics supposes an absolute space, an absolute time, and an infinite, that is, an infinitely variable velocity. Transformations of measurements from different systems of reference, spatial or temporal, can be simply and arithmetically calculated and expressed as variations of velocity. Euclid's postulates are applicable and universally valid. Observational deformations of Euclidean figures are apparent, not real, and easily explicable as perspectives due to the conditions of the observer. Let me illustrate it by supposing that I travel, say, from London to Edinburgh, in a slow train while you travel the same route by an express. The space and the time have not varied. They are identical for each of us, but the apparent stretching of the space and time for me, and their apparent contraction for you, are simply adjusted by taking into account the velocity of the train, say 30 miles an hour for me, 60 miles an hour for you. We express this relatively by saying that we have moved through the same space, you in half the time lived through by me. This is the commonly accepted principle. The new principle of relativity has two stages, the special principle and the general principle. The difference is not intensive but extensive. The first was confined to a definite phenomenon, the velocity of the propagation of light in vacuo. The second is the application of the same principle to all laws of nature. The special relativity principle is based on the fundamental concept that space is variable and that time is variable, and that there is one finite velocity which is constant and also a limiting velocity. That is, a velocity which cannot be exceeded, but to which the approach is infinite. This constant velocity is that of the propagation of light. The concept of this velocity as constant and as a limit is not as arbitrary as it at first appears to be uninitiated. For as a matter of fact, we are absolutely dependent on light signals for sending messages or measuring distances or estimating intervals between events. The special principle of relativity is that observers in systems moving uniformly in relation to one another do not use the same standards in measuring space and time dimensions, but each observer employs a standard which supposes his own system at rest. When then there are observers of the same events in a different system of reference, moving uniformly relatively to one another, as in the two trains, each observer sees the light signals propagated with the same velocity, but the difference due to the movements of the two systems, relatively to one another, is in the space and time which are different. It is easy to illustrate. Let us go back to the two railway journeys. According to the classical mechanics, one is double the velocity of the other. According to the principle of relativity, the velocity of each is identical, because in each train the observer is at rest and the velocity therefore zero. The difference is in the space and the time. These are elongated for the traveler in the slow train, shortened for the traveler in the express. To common sense this appears contradictory, but reflection will show that it is a simple alternative to the common sense view and logically an exact equivalent. It is simply equal to saying, what is also a fact, that in our two journeys neither I nor you moved at all, but our destination moved to us, and in doing so was twice as long in coming to me as it was in coming to you. The special relativity principle was confined to the consideration of observers in systems of reference in uniform movement of translation relatively to one another, as for example in the two trains. The general relativity principle is the extension of the special principle to non-uniform systems, in particular to rotational systems, and it affects the concept of the laws of nature. It declares that when the movement of a system relatively to other systems is non-uniform, the particular quality which the observer experiences as influence or force can find an equivalent expression in the motion of the system for an observer in another system. The rotational movement, which seems to us to generate a centrifugal force balanced by a centripetal force, may appear to another observer as a gravitational field whose purely metrical properties determine the direction of masses moving therein. It further deduces that for all non-uniform systems, the spatial coordinates, length, breadth, depth, are not Euclidean. In a gravitational field, space for all observers is warped or curved. We all know the curiously unpleasant feeling of acceleration we experience when we are walking along an apparently level passage, which is really a gradient. It seems as though a force is pulling us, whereas the whole phenomenon can be explained by the geometry of the gravitational field. For the moment, I am trying to state what the principle is without explaining the grounds for adopting it. Thus, to return to the illustration of the train journeys, in the two previous uses of the illustration I supposed the movement uniform, and there was consequently little difficulty in showing that it is exactly equivalent to regard the train as not moving and the destination moving, or to regard the train as moving and the destination as fixed. In the one case we shall say that the space and time vary and the velocity is constant. In the other, that space and time do not change, but velocity does. But now suppose that the train is brought to a stop by the sudden application of the brakes, and that the traveler is thrown heavily from his seat. There will be difficulty in making him take the wheel that he was all the while at rest, and it was the seat which moved from him and the floor which moved towards him. Yet, this is exactly how it might appear to an observer in another system, and in so describing it, he would have an equal right to declare it true. Suppose then we understand the principle and accept it to the extent of admitting that we can, if it is worth our while, always find an equivalent way of describing the phenomena of movement in place of the one to which we are accustomed. Is it then, we shall ask, merely a matter of choice? If not, what is the necessity for disturbing our ingrained common sense principles? The reply is not an argument, but an experiment. The experiment which has occasioned the revolution in our fundamental concepts and called for the formulation of a new basis of a philosophy of nature was carried out by Michelson and Morley in 1887 and is described in the Philosophical Magazine for December of that year. It has been so often described since that it will be sufficient to allude to it here and go straight away to the principle of it. Since Newton, and on the foundations he had laid down, there has been a steady and continuous evolution of scientific knowledge, marked by an ever-widening range, an ever-deepening insight, and an ever-surer inclusiveness. The theoretical objection to his theory of gravitation, that the concept of action at a distance which it involved is a concept of something wholly unimaginable, was made by Leibniz. Newton himself felt the force of the objection, and to meet it supposed that space might be filled with a subtile ethereal matter. The theory of the ether of space became a necessary hypothesis, however, only when the undulatory theory of light was formulated. With the extension of the discoveries of electromagnetic phenomena, this ether tended to become one of the fundamental concepts of science. It was, however, purely conceptual, and the famous Michelson-Morley experiment was contrived with the primary intention of testing its reality as a physical existence. The principle is easily explained. The Earth is in a movement of translation relatively to the Sun amounting to about 30 kilometers a second. If then we consider the Earth as at rest, we must suppose the ether to be streaming through it at the equivalent velocity. Now it is easy to calculate the difference in time required for any given uniform propagation to reach a point and return in a direction which crosses the stream, and to reach and return from an equally distant point in the direction of the stream. Thus let us suppose, for instance, that the stream is flowing 30 kilometers a second, and that our signal unretarded would travel 50 kilometers a second, and that we project it to a measured point in each direction, up the stream and across it, from which points it is immediately reflected and returns to us. Across the stream, the flow will be equal to a retardation of 10 kilometers a second. Our projectile will therefore travel 40 kilometers in a second and will return in the same time. That is, it will go and return in 2 seconds. Now suppose it is directed upstream. It will have the full retardation and therefore will travel only 20 kilometers in the first second, and to arrive at the measured point, 40 kilometers. It will require 2 seconds, the same time in which, across the stream, it went that distance and back. It is true it will return in half a second, for it will have the 30 kilometers a second added to its own velocity of 50, but it will be the half second later than the other. In the actual experiment, a beam of light was sent to a mirror and reflected back along each axis. Light has a velocity approaching 300,000 kilometers a second, but the calculation was worked out to an accuracy and within a margin of error which made it still quite certain that the retardation would be revealed. To the great surprise and deep disappointment of the experimenters, the result was negative. along each axis the return was simultaneous. This was a famous experiment. Let us now look at its consequences. In the first place is negatived the ether hypothesis. There is no ether if by ether is meant something occupying space and at rest relatively to the matter which moves through it. If there be ether, it must move with the system which is in relative translation, exactly as Descartes supposed. If to suppose an ether is to suppose infinite ethers, then the hypothesis is useless and may be dismissed. A second consequence is that we must suppose the velocity of light in vacuo to be unaffected by the movement of the source. This is more fundamental still, for if there be no ether, or if the ether be perfectly frictionless, the velocity, when the source is moving, ought to be different from the velocity when the source is at rest. Yet the experiment proved it to be the same in each case. A third consequence is that as the laws of nature remain constant for observers in moving systems, the space and time dimensions, in order to keep the ratio constant, must themselves vary. A hypothesis to account for the negative result of the experiment was put forward independently by the late G.F. Fitzgerald, professor in Trinity College, Dublin, and H.A. Lawrence, professor of physics in the University of Leiden. It is generally known as the Lorentz-Fitzgerald contraction. It assumed that the dimensions of a solid body moving through the ether undergo slight changes, that the moving body is automatically contracted in the line of direction in which it is moving, and that this contraction is exactly equivalent to and counterbalances the difference which would otherwise be manifested in the velocity of light. It will be seen that such hypothesis is primarily nothing but a simple ad hoc device for giving expression to the negative result of the experiment, and is little more than an acknowledgement and way of stating positively the fact observed. It has, however, been possible to submit the question whether there is in reality, or as physical fact, such a contraction, to laboratory test by measuring the electrical resistance of metal rods, both across and in the direction of their translation. These experiments have proved negative and have caused the abandonment of the hypothesis by physicists, insofar at least as it purports to be the actual explanation of the phenomenon. The contraction theory of Lorentz, however, is more fundamental than that of Fitzgerald, and consequently maintains its place in the relativity theory as an alternate way of expressing the fact mathematically. Fitzgerald conceived the contraction as affecting the moving mass as a whole. Lorentz conceives it as occurring in the electron, and therefore as bound up with the physical constitution of the universe. An electron is theoretically physical. That is, if we suppose it removed from any external influence, it would be a perfect sphere. But in fact, it moves in an orbit around a central nucleus, and the whole system of the atom, of which it is a constituent part, may be moving relatively to other atoms. Lorentz, therefore, supposed that a flattening of the spherical shape in the direction of the movement might be a fundamental condition of its constitution and of the system generally. Such contraction would easily account for the constancy of velocity when a movement of translation is compounded with a movement of propagation. A much more radical interpretation was given by Hermann Minkowski in 1908, shortly before his death at the age of 45, in an address on space and time, which has since become historical. In it he formulated a new mathematical theory, which embodied in a complete form the principle, the necessity of which had been revealed in the negative result of the experiment. Minkowski proposed a new mathematical scheme of the universe in which time entered as a dimension. The universe is to be conceived not, as hitherto, as a three-dimensional continuum enduring in a one-dimensional time, to which it is indifferent, but as a four-dimensional continuum in which the three dimensions of space and the dimension of time are the axis of coordination, by which the observers in systems of reference moving relatively to one another relate the constituent factors of the universe. That is, the events the assemblage of which is the universe. The beauty of this theory is that its apparent strangeness, when first propounded, tends to give way to familiarity and obviousness. For when we come to think of it, we recognize that the world of our living experience is four-dimensional. The opening sentences of the address, delivered at Cologne on September 21, 1908, have been often quoted as marking the beginning of a new epoch in physical theory. The observations concerning space and time, which I am about to expound, are the results of experiments in physics. Therein lies their strength. They go to the roots of matters. Henceforward, space and time as independent things must sink to mere shadows, and the only thing which can preserve some sort of subsistence is a kind of union of the two. He then developed his argument. The universe must be conceived as an assemblage of events. An event is determined for every observer from the standpoint of his system of reference, and in relation to that system, by four coordinates, 3 for space and 1 for time. Suppose two events to occur. Observers in one system of reference will measure a certain distance separating the two events in space and a certain interval separating them in time. These measurements will not accord with those made by observers in other systems of reference, who will measure the same events from their own standpoint and will find different distances and different intervals. Each observer will keep constant the ratio between his coordinates of measurement in passing from one system to another, but the four axes themselves will each undergo variation. The simplicity of Minkowski's scheme won for its general admiration and made the adoption of the principle of relativity easy in mathematics. A fourth dimension of space has hitherto been always associated with the attempt to rationalize the claims of spiritualistic phenomena to actuality. But Minkowski showed that the fourth dimension was necessary to explain experience on the ordinary common-sense plane. Einstein, referring to his four-dimensional theory of Minkowski, writes, "A mystical shudder seizes the non-mathematician when a fourth dimension is spoken of, a creepy emotion, something like that produced by a stage effect. Yet, there is no more obvious commonplace than that our world of everyday experience is a four-dimensional space-time continuum. It is from Minkowski's scheme of its geometry, of a four-dimensional world, that we get the definitions of world point and world line, which play so important a part in the theory of relativity. Space and time are linked together as indissolubly, and are as interchangeable as the three rectangular dimensions of space in the Euclidean geometry. Yet, in ordinary intuition, space seems to us to be entirely different from time, and the difference to be qualitative and not quantitative. It seems to us, that is to say, that the process of the world is taking place in space and going forward in time, and it is this complete separation which has always made our apprehension of movement and change impossible to rationalize whenever we have tried to analyze it logically. Yet, our actual perceptions are always concerned with places and times bound together. A place does not exist for anyone except at a time, nor does any time exist except at a place. Minkowski proposed then to recognize this indissoluble union, and he named a point instant determined by 4 coordinates as a world point. The manifoldness of all imaginable world points is then what we call the world. An event is what we observe at a world point, and we coordinate it with other events at the other world points by the 4 world axes. We have to imagine something existing at every world point. This is a condition of our perception of a world. And when we identify this existence as passing from world point to world point, we generate for it a curve or line. This is the world line. A world line is not a line in space occupying time, but a line in space-time. World points and world lines are not the world events we observe. The event which is observable is the intersection of world lines. These intersections may be infinitely complex, may be twisted into most intricate knots, and may appear infinitely different according to the space-time system to which they are referred. There is a very important consequence of this 4-dimensional metric system. As its axes of coordination are relative to a frame of reference, and as this frame of reference is always, for the observer attached to it, a space-time system at rest relatively to other systems in movement, it follows that this space-time system will differ from one another in their time direction as well as in their space direction. We represent our time direction by joining 2 cones, one of which opens into the future and the other into the past. The future contains all the world points which belong to the active future, the second all that belong to the active past. For every space-time system, the time direction is perpendicular to the space direction. Space, that is to say, cuts the point of intersection of the 2 cones and is perpendicular to their common axis. And for every observer in the space-time system considered at rest, the space direction is horizontal and the time direction vertical. It follows that the world line of space-time systems moving relatively to one another will intersect in their time direction as well as in their space direction. We are not only unable to give any meaning to simultaneity, but we have to reject it as a fact and explain its appearance as subjective illusion. To return to the actual experiments, there was a deduction from them which presented the aspect of complete paradox. This was the constancy of the velocity of light for all observers and its independence of all variations in the relative velocity of a system. The velocity of light in vacuo is 300,000 kilometers a second. It is a finite velocity, and no velocity is known to exceed it. Some of the radioactive substances give off particles which approach it, the beta particles. But though they attain to 99% of the velocity, they are not known to reach it. Now suppose that relatively to ourselves there is a system being translated at the rate of 15,000 kilometers a second. We must suppose that for observers in this system, as for us, light is propagated at the uniform finite velocity of 300,000 kilometers a second. This appears a direct self-contradiction. How is it to be reconciled? However surprising it may be to have acknowledged that we can find no evidence of the absolute movement of a material system, nor discover the direction of that movement by experiments made within the system, it is more than surprising, for it seems downright absurd, to affirm that a finite velocity is identical for all observers in all systems of translation, uniform or non-uniform in relation to one another. It is in regard to this problem that the work of Einstein is particularly important. His philosophical attitude toward this paradox is especially deserving of notice. Einstein from the first accepted the negative result of the experiment. It did not for him indicate an agnostic position. It did not merely mean that an absolute movement or movement measured from an absolute or fixed zero is unknowable. He accepted the negative evidence as definite proof of the non-existence of an absolute standard, and he proposed to reject the postulate that an absolute standard is a necessity of thought. But how is the rejection of absolute movement compatible with the affirmation of a constant finite velocity? According to Einstein, this incompatibility is purely apparent. In fact, it is compensated by the deformation of the axis of coordination used by one observer as seen by another. Thus, to an observer in a system moving relatively and uniformly to us at half the speed of light, our proportions are foreshortened to half what they appear to us, so that measuring the propagation of light, our unit is double that of his, and his is correspondingly half that of ours. Each observer therefore finds the light propagated at the same velocity of 300,000 kilometers a second, but the kilometers used by the one appear to the observer in the rapidly moving system elongated to double their length, and those used by the observer in the rapidly moving system appear halved in their proportion to the observer in the slow-moving system. The special principle of relativity, which Einstein formulated in 1905, had in view his problem, but only in regard to the velocity of light and its independence of the movement of the source. Already, however, it has seemed to him that if this principle be true, it is not limited in its application, and it probably implies an entirely new conception of physical reality. The general principle of relativity, which formulates a new law of gravitation in place of the law of Newton, is the result. It is not based on a new experiment, but on an application of the principle of the original experiment to all the laws of nature. It is simply, as applied to gravitation, that the phenomenon of weight and the acceleration of a falling body is completely explained by the geometry of the gravitational field, and that the law of gravitation may be formulated in terms of the stresses or, as they are named, the tensors, which constitute the field. Tensors are a class of mathematical functions which enable us to specify relations without reference to any particular coordinate system whatever. They express physical relations in a form which is independent of particular coordinates employed. In 1917, Einstein had thought out the three means by which his new theory could be brought to the test. First, that it would account for the discordance of the motion of the perihelion of Mercury, as calculated on the Newtonian formula, and as it is found to be in fact. Its cause has been sought for in vain in the supposed presence of a mass of matter between the orbit and the Sun. It has also been suggested that the Newtonian law may require an infinitesimal alteration to its mathematical formula to make it bring out the result correctly. But the idea of the existence of an unknown minor planet is now generally agreed to be so improbable as almost to amount to the certainty that there is none. And an alteration of the mathematical formula to make the calculations of Mercury's period come right would make other calculations work out wrong. In this case, Einstein's theory based on the principle of relativity has been so triumphantly vindicated that to many mathematicians and physicists, it is sufficient of itself to establish the principle. Einstein's formula gave the exact result without upsetting the calculations in any other case. The second means, was the displacements of stars in the gravitational field. He predicted that the light of stars near the Sun would be deflected and that deflection would be twice the amount which Newton's law calculated for the mass and velocity would give, if light, as Newton thought possible, had mass. This prediction was verified in the observations of the Eclipse expedition of May 1919 and was the occasion of the extraordinary public interest in the new theory. The third means proposed has so far not passed the test and is the subject of research and of much discussion. I will now try and explain by illustrations what the new principle is. Let us suppose then that from the window of a smoothly traveling railway carriage a stone is dropped, and that an observer in the train watches it fall. For him it follows a straight course to the ground. An observer watches the same events from a position which is fixed in respect to the moving system of the train. For him it follows a curve. Which is right? Is there a real straight line which is the shortest distance between 2 points? Is there any way by which each observer can so correct his observation that he can discover the real as distinct from the apparent line? The principle of relativity declares that there is no way of deciding between the two observers, that each must use the coordinates he carries with him, and that these adapt themselves to accord with every system of reference he enters, and that each observer therefore measures an event from the standpoint of his own system, regarded as at rest. From this it follows that an event, dropping the stone from the carriage window, which for one observer occurs in one and the same place, for another observer has its beginning separated from its end by a distance in space. If we consider the whole event as a single, then the point at which it is observed from one system of reference will not correspond with its place as observed from another. It follows therefore that every straight line is what in geometry is named geodesic. It is the shortest distance between 2 points, having regard to the space curvature of the system to which it is referred. This is the principle of relativity as it applies to space. Now suppose that time, not space, is in question, and that observers take positions equidistant from the point where an event is to take place for the purpose of recording it simultaneously. Let two observers be placed at an equal distance from a point on an electric railway at which it is arranged that a break in the circuit shall be indicated by a flash. Each observer will see the flash at the same instant. Suppose now that two other observers are similarly situated, but on the moving train instead of on the permanent way. It is true that in such case, as the timing is with light signals, it will not be possible to make any difference appreciable. The velocity of light is so disproportionate to any conceivable velocity of the train that the effect due to that difference could only be expressed in thousands of millions of a second in time, or of an inch in space. But all the same, the principle can be made clear by the illustration. If the precise movement of the emission of the signal, the electric spark, is the same for two observers equidistant on the permanent way, it cannot be the same for two observers equidistant in a moving train, because during the propagation, one observer will have advanced to meet the signal, the other will have receded, giving it a correspondingly longer route to travel. We have only to imagine the journey to be from the Earth to the Sun and the velocity to be that of light, and then the two signals which, for the observers on the moving system, are simultaneous, will be separated for the stationary observer by an interval of about 8 minutes. The principle of relativity is therefore simultaneity has no absolute meaning. No two events which happen at the same moment for observers on one system of reference can be simultaneous for observers in another system. Therefore, two events which for one observer are simultaneous for another are before and after. So far, we have been following the special principle of relativity. It teaches us that, contrary to the notion of classical mechanics, according to which all differences in the observations of events and all differences in the appearance of events to the observers are calculable in terms of a constant space and time and a variable velocity. There is no distance in space and no interval of time which is invariable and independent of the system of relative movement to which the observer is attached. It takes us a long way in the direction of a new coordination of nature on a philosophical principle, but there is nothing in it peculiarly subversive of our ordinary concepts. Indeed, to many mathematicians, it commended itself at once as seeming to offer a much better scheme on which to undertake the organization of the science of nature. When, however, the principle is applied not only to systems moving uniformly in relation to one another, and to phenomena inappreciable in ordinary experience, such as electromagnetic propagations, but also to gravitation and the ordinary laws of nature, it touches the science and mathematics of common life. It is then that it disturbs our feeling of at-homeness in the universe, brings over us a feeling of giddiness and makes it seem impossible at once to attain a new equilibrium. There is something fundamental in our experience of weight. Without it, the world would seem to have no substance. Without it, we should feel like the man in the folktale who was induced to barter his shadow. Now it is easy enough to imagine that the phenomena of gravitation may be unknown to observers in other systems, but to suppose that they may observe the identical phenomenon which we experience as weight and yet observe it not as weight but as the movement of the system, and that this movement is the exact equivalent of what we experience as force, this is very difficult to accept. It is precisely this that the general principle of relativity affirms. Suppose, to take one of Einstein's illustrations, a room such that in which the reader may be sitting to be detached and transported bodily into some distant region so remote from masses of matter that it is entirely free from any force of attraction. Let us suppose no gravitational field. We shall have to think of it as artificially held together and the objects in it as fastened by cords or such like means, for the loose objects it might contain would follow the direction of any chance movement which might be imposed on them. If we supposed ourselves still sitting or standing on the floor, it will not be by reason of our weight, but by attachment or holding on. Let us now imagine that this room is attached by a hook to a cord outside, which is being pulled, thereby drawing the room in a definite direction. The hook being attached to the ceiling, the definite direction of the ceiling will be upwards. At once, all loose objects will lie and remain lying on the floor, and free suspended objects will hang downwards. And we, if we would rise from the floor, will have to put forth an effort sufficient to produce a movement in excess of the dragging movement. To us in the room it will seem then that the objects have suddenly become heavy and that they fall downwards by their weight, but to observers outside the whole phenomenon it will be a simple consequence of the dragging movement, and explicable in terms of it. If an object is detached, it will not, as seen by the outside observer, fall on the floor. It will remain immobile till the floor reaches it. This is what Einstein means by equivalence. What appears to be the observer in a rotating system as weight, that is as the attraction of the object to the center of the rotating mass, will appear to an observer in another system as the movement of the rotating mass to the object at rest. Our ordinary interpretation of the phenomenon which we term gravitation is that it is due to the mutual attraction of masses. But so far as our Earth alone is concerned, there is an exact equivalent way of interpreting it. We may attribute it to the centrifugal and the centripetal forces generated by rotation. Again, the exact equivalent of rotating Earth and fixed firmament is an Earth at rest and a revolving firmament. So then, an observer of a falling body, Newton's apple for example, may say that the object does or does not move. It simply depends on whether from his standpoint the Earth is rotating or the firmament revolving. If now we conclude with the Earth's rotation also its translation, then we have a system of relative movements in which to one observer the apple will seem to fall to the Earth, to another the Earth will seem to rise to the apple, while yet another, situated on the sun or fixed star, the whole order of the event may be reversed, and the Earth may seem to move from the apple, or the apple from the Earth, according to the direction of the various movements relatively to the observer. All these observations are contradictory on the interpretation that the movements are caused by the physical attraction of masses, but all are reconcilable on the interpretation that the movements are determined by the geometrical structure of the gravitational field. This enables us to see what is meant when it is affirmed that the space in the gravitational field is non-Euclidean. In the gravitational field, the observer is either at rest in the firmament relatively to the rotational system, or else at rest on the rotational system relatively to the moving firmament. In neither case can Euclid's postulates be fulfilled, or Euclid's axioms hold true. Consider, for example, the postulate that a straight line is the shortest distance between 2 points. The shortest distance for one observer will not be the shortest distance from the other, or, what is the same thing, the straight line drawn by one will appear curved to the other. But when we realize this relativity, can we not make allowance for the appearance to different observers and work out the perspective law for each? This is what we imagine we are always engaged in doing. Is it not a commonplace of psychology that visual space is not real space? The principle of relativity shows us that this supposed power of correcting appearance by reference to an intellectual absolute is illusion. The illusion is persistent. It is so easy to represent our system of reference in movement by means of our imagination, that we have come to cease to think of the firmament as in movement, and though it appears so, we translate the appearance automatically into the reality of our own movement. Can anyone really think the smoothly running railway carriage is at rest while the landscape is in movement? We fail therefore to see that though our imagination aids us in representing our own movement as relative, it never brings us to a system at absolute rest. That necessary standpoint of a system at rest must be within the observer himself and is the condition of his observation. It is from that standpoint that our measurements are made, and we carry with us, attached to us, inseparable from us, the axis of coordination which we apply to the universe. We are therefore perpetually under the illusion that the absolute criterion lies without us, whereas it is indissolubly part of our nature. It is just as if we suppose the center of a circle to be independent of its circumference and free to move about within it, even indeed to come outside and survey it. Common experience offers us an example of a persistent illusion in regard to space. we think that we know by actual experience real space. But the space we think real is not the space we perceive by any of our senses. We do not think, for example, that the sun and the moon are in reality the same size as a 3-penny bit, though they cover the same amount of visual extension as this object held at arm's length. The space we think real is purely conceptual and ideal, and this place is Euclidean. We do not encounter it in experience, nevertheless we are convinced it really exists, and suppose it must underlie and condition our experience, and we distinguish it as a noumenal from the phenomenal. It is this persistent illusion of real space, noumenal, not phenomenal, which makes it so disconcerting to us and so difficult to accept the notion of space, which may be curved, warped, or distorted, not in its appearance only, but in reality. It is a formation of space with such properties that make the general principle of relativity appear paradoxical. If, however, we accept the negative result of the physical experiments, we are bound to reject as pure illusion the notion that Euclidean space exists beneath the world of sense perception. We may make the concept of curvature in space clear by simplifying for the purpose of illustration the scheme of the principle. Let us suppose then that instead of manifold gravitational fields, there exists only one. Let us abstract, that is to say, from everything in nature except in rotating Earth and the surrounding extension relative to it, which we will call the firmament. The gravitational field will now consist of 2 and only 2 systems of reference. An observer at rest on the Earth sees the firmament in a continuous movement from east to west. An observer in the firmament sees the Earth rotating on its axis from west to east. The surface of the Earth will then be the center of a gravitational field, and the limits of this field will be the Earth's axis on the one side and an external imaginary limit of space, purely Euclidean, on the other. It is clear that within this gravitational field, space must be warped, because every observer will be at rest on one of the 2 systems. Any movement, therefore, be it of propagation or of translation, which takes place in the gravitational field, must be occurring in the space of one of the systems. Suppose then any object to be detached from the rotating Earth. It at once takes its place in the circulating firmament. Similarly, any object detached from the firmament takes its place in the rotating Earth. The universal space simply denotes the continuity of these 2 systems in the relation of movement and rest for one another. Space is not a third somewhat in which these movements are taking place. To affirm it would simply be to deny the reality of one of the movements, and what possibly ground can there be for that? The essence of the principle of relativity is the explicit denial of such an absolute space and the recognition of the impossibility of interpreting facts on the supposition of its existence. The curvature of space is therefore physical fact, not subjective appearance. Now let us suppose a straight line drawn from within the Earth system to any point in the firmament system. The course of that straight line must be its spatial condition, curve in its part through the Earth system and curve in the reverse direction when it passes through the firmament system. Any line which is the shortest between 2 points for an observer in one system will not be the shortest for an observer in the other. Someone may still object. He may demur that my conclusion that there is a real curvature of space in the gravitational field follows only because I have started with an arbitrary hypothesis that the universe is a single gravitational field. The reply is that the conclusion does not depend on this hypothesis, and it is only introduced for simplicity and to enable attention to be directed on the essential point. Admit that the universe is infinitely complicated, that it consists of infinite systems moving uniformly and non-uniformly relative to one another. This only increases the difficulty of correlating observations. No doubt, this difficulty has been the guiding motive in the evolution of the concept of absolute space, but it is not a proof that absolute space exists. 300 years ago, it was discovered that a heavy body such as lead and a light body such as wood follow the same identical course in the same identical time in the gravitational field. When allowed to fall with the same initial velocity and with all frictional obstructions removed, as for example in the vacuum produced by an air pump. The significance of this discovery was never thought out. It is precisely what is affirmed by the theory of equivalence. Why does a stone fall to the ground when let go? The usual answer is because it was lifted off the ground, and the hypothesis in that answer is that the earth exercises a direct influence on the stone, called the force of attraction. The strength of this force was found to vary with the distance according to well-known Newtonian law. As an explanation, this has not satisfied modern physics because it admits the notion of action at a distance. The advance in the study of electromagnetic phenomena has led to the conclusion that there is no action at a distance. When we see a magnet attract a piece of iron, science will not let us be satisfied with the simple explanation that the magnet draws the iron across empty space. Science requires to see in the phenomenon a property or a character of the intervening space, which it names the magnetic field. It is this and not the magnet which influences the iron, causing it to move toward the magnet. In gravitation, we have the exact analogy and at the same time an important contrast. The contrast is that in gravitational field, as Galileo's experiments proved, bodies undergo an acceleration which does not depend on their material or constitution. And in this way, the principle of relativity explains gravitation, showing it to be a phenomenon which depends on relative systems of movement and on the position or standpoint of rest, necessarily assumed by the observer for his own system. What kind of world is it then that we live in? A world which is finite insofar as the concepts of space and time determine it, and which yet is not circumscribed. The principle of relativity enables us, without doing violence to the laws of thought and without contradicting experience, to dispute the Euclidean axioms. Space and time, which throughout the whole history of philosophy have been the stubborn realities of the framework of the universe, baffling the mind in every effort to form a consistent scheme of nature, are deposed, at least from their dominating position in the mathematical and physical sciences. It is a triumph of philosophy, for the principle of relativity is a return to the concept which Leibniz indicated and which was abandoned by the scientific successors of Newton. In nothing is the contrast more striking than in concept of space. For Newton, space is an infinite, absolute immensity, which can only be present to the perception of an infinite God. For Leibniz, God alone of intelligent beings is wholly without the perception of space, because God is conceived as an intelligence with adequate ideas and with no obscure perceptions. Let us drop the theoretical expression and state the same contrast in scientific terms. We shall then say that for the materialist, space is the fundamental reality and the universe presupposes it. For the relativist, On the other hand, space is a limitation of the observer's apprehension of the universe. Infinity is not the affirmation of space, but its disappearance.